Alrighty, good evening everybody. Today we're going to be talking and learning about VSEPR theory. So what is VSEPR? VSEPR, which technically, yes, should be pronounced VSEPR, but it's easier for us to say VSEPR, stands for the valence shell electron pair repulsion theory. And so what VSEPR theory does is it helps us to predict the shape of molecules based on how their atoms are interacting and the electrostatic repulsion they experience from each other. So when you put atoms into a molecule and you try and force them to bond, what you do is their valence electrons, while both interacting in the form of making bonds, they also actually repel each other. So it's not just an interaction, a positive interaction to form bonds. They actually try and push each other away. And so those electrons, since they're all negatively charged, will want to push each other away, and they tend to orient themselves so that they have the furthest distance between the atoms as possible. And so VSEPR theory allows us to see when we have X number of molecules, then what that is going to look like in order to get as far apart from each other as possible. So VSEPR theory, and I keep spelling VSEPR wrong, and I'm sorry, it's VSEPR. We'll fix that later, sorry guys. So the way that we kind of look at this is we look at it in a couple different classes. So we look at the total number of groups that are bonding, the number of bonding pairs, the number of lone pairs, the AXE class, which is something I'll explain later, the electron geometry, and the molecular geometry. Those are two different things. So when we're talking about the total number of groups, we're talking about the number of atoms around the central atom as well as the number of valence electrons around that central atom. So if we have two atoms around the central atom and we have two bonding pairs, meaning that those two atoms each form a bond with the central atom, and we have 0 lone pairs around the atom, we're considered an AXE class of AX2E0. where the 2 by the X stands for the number of bonding pairs, and the E stands for the number of lone pairs. So 2XE0. So the electron geometry is going to be linear. It's going to go in a straight line, right? We're going to be as far apart from each other, meaning we have 180 degrees here. The molecular geometry will also be linear. We only have two things, so it's going to be A surrounded by two B's, okay? And they keep as far away from each other as possible. So the electron geometry takes into account both the bonding actual elements that are bonding as well as the electrons that are there as well. They take into account electrons around that central atom. Not around these B's, but around the A. The central atom, not the exterior atoms. The electrons that we care about are only those around the central atom. So if we have 3 groups around the central atom, and 3 of them are bonding, and none are lone pairs, we have an AX3E0, which for the electron geometry is called trigonal planar. And so it also has a molecular geometry of trigonal planar. Now, there's another kind of AXE class that we can have, and that would be 3 groups around the central atom, where 2 of them are bonding, and only 1 of them is a lone pair, and this would be an AX2E1 group. Its electron geometry is also going to be trigonal planar. However, its molecular geometry is going to be different. It's going to be called bent. And so let's look at those trigonal planar. So the electron geometry of 3 groups, trigonal planar, looks like this, where you have a central atom with 3 groups going off of it. Here they can either be 3 bonding groups or 2 bonding and 1 lone pair. Now, if the molecular geometry is also trigonal planar, then this is going to be 3 bonding groups. An A central atom surrounded by 3 bonding groups. If, however, our molecular geometry is bent, then what we have going on is we have 1 central atom with 2 bonding groups and 1 lone pair. Okay. We can also have 4 groups around the central atom. And we can have 4 groups with 4 bonding pairs and 0 lone pairs, which is an AXE class of, you guessed it, AX4E0. Now the electron geometry on this is actually called tetrahedral, which you guys should recognize tetra from our list of prefixes, mono, di, tri, tetra. Tetra is 4, so tetrahedral. The molecular geometry, if we have 4 bonding pairs and 0 lone pairs, is going to be the same as our electron geometry, tetrahedral again. Now, if we have 4 groups around the central atom and only 3 of them are bonding pairs and 1 is a lone pair, then we have an AXE class of AX3E1. Our electron geometry is still the same. It's still a tetrahedral electron geometry because we still have 4 groups around the central atom. However, our molecular geometry has now changed. We now only have 3 groups that are bonding and 1 lone electron. So that becomes trigonal pyramidal. Okay? And we're going to show you what that looks like in a second. If I have 4 total groups of 4 total groups around the central atom, and only 2 of them are bonding and 2 of them are lone pair, we now have an AX2E2 class, where the electron geometry, again, since we have 4 groups, it's still tetrahedral, but now our molecular geometry has changed to only 2 bonding and 2 lone pairs, and so it is again that word that we've heard before of, bent. So let's talk about what the electron geometry of tetrahedral looks like. So if we have a tetrahedral geometry, right there it flashed, look at that pretty animation. Our geometry looks something like this, a tetrahedral. So we have a central atom right here with 1, 2, 3, 4 bonding groups off of it. Now these can be bonding groups, they can be lone pairs, but there are 4 groups around the central atom. 1, 2, 3, 4. Now, if we have 4 bonding groups, we are still, as a molecular geometry, tetrahedral. Okay? And so what that looks like is exactly what it looks like over here. A central atom with 1, 2, 3, 4 bonding groups off of it. Sorry, I had to kind of cram it in there so it looks a little small. But they're all going to be as far away from each other as possible, keeping equal distance away from each other, which is why it creates that kind of tetrahedral look. It's a triangle, but they're all like as far away as possible. If we're looking at just having 3 bonding pairs and 1 lone pair, that trigonal pyramidal, what that looks like is it looks remarkably like the tetrahedral, except this top bond is, again, lone pairs. It's not a bonding pair. So we have the central atom with 1, 2, 3 bonding pairs and 1 lone pair. And then if we have 2 bonding pairs and 2 lone pairs, we are bent. And what that looks like is the same kind of idea of a tetrahedral, except here it's A with 2 bonding pairs and 2 lone pairs. So they are going to stay as far away from each other as possible, still in that tetrahedral area, but now we're called bent for the molecular geometry. So in class tomorrow, I'm going to give you a sheet that has all of this information down, but this is something that you need to kind of start getting your head around. This is something that we're going to be carrying into and using in the future. The shape of molecules matters greatly with how they interact with each other, and so this is really important. So let's talk about some examples. Let's talk about methane, or carbon tetrahydride, and water, or dihydrogen monoxide. So let's fill in this table for carbon tetrachloride. We've got a carbon central atom and 4 hydrogens that are bonding around it. So the total number of groups around our central carbon atom would be 4. Okay? The number of bonding pairs, since there are 4 hydrogens around 1 carbon, they are all bonding to the carbon, so we should have 4 bonding pairs. This means that we would have 0 lone pairs, which makes our AXE class AX4E0. With an AX4E0 class, we know that our electron geometry is going to be tetrahedral, where it looks like our nice little tetrahedral, and our molecular geometry is going to be the same. It's going to be a tetrahedral, looking like this, CH4. Okay? Let's talk about water. Let's talk about the total number of groups around hydrogen. So oxygen is bound to hydrogen twice, but oxygen, remember, from our Lewis structures, or Lewis diagrams, we know that oxygen likes to form 2 bonds and have 2 lone pairs around it. So we know that oxygen is going to have 4 total groups in order to complete its octet. 2 are going to be bound to hydrogen, and then you're going to have 4 total electrons, or 2 lone pairs around that oxygen. So our total number of groups is going to again be 4, However, the number of bonding pairs this time is 2, those 2 hydrogens, and the number of lone pairs is going to be 2 for those 4 lone pair electrons to complete oxygen's octet. So it's going to have an AXE class of AX2E2. Its electron geometry, since it's got a total number of 4 groups, it's still going to be tetrahedral, right? It's still going to look like a tetrahedral electron-wise. Its molecular geometry, however, AX2E2, is bent, and so it's going to be oxygen bound to 2 hydrogens with 2 lone pairs up on this end, creating a bent shape, which is why this is not linear, even though it's only 3 atoms involved. It's not linear because those electrons take up the space of where those other bonds would be if it was tetrahedral and molecular. Okay? Alright, I'd like you guys to take a minute and practice some. So I would like you guys to figure out what the shapes of carbon dioxide, the carbonate 2- ion, and ammonia would look like. I would like you to complete this table. So I'd like you to pause and fill in this table for all 3 of those examples. Okay, so pause for a minute. I'm going to take a deep breath, and you're going to pause it, and then I'm going to press play, and you're going to press play afterwards, and I'm going to start talking. Okay, we'll check our work together. So pause the video and start working it out. Okay, I hope you honestly paused it and did this work. I can't force you to, but I really hope you tried it yourself. So let's check your work. So if we have carbon dioxide, the total number of groups around carbon would be 2, right? Just 2 oxygens. Now the number of bonding pairs then would be 4. The number of bonding pairs should actually be, oh yeah, sorry, just 2. Just 2. We've got oxygen and oxygen. Here, double bonds are considered 1 bonding pair. The number of lone pairs would be 0. So we've got AX2E0. This is linear and linear. Okay? So what it's going to look like is carbon doubly bound to oxygen and oxygen with 2 lone pairs. Now, number of lone pairs is still 0 around carbon. Yes, there are 2 and 4 lone pairs, but those are around oxygen. And remember, we only are concerned about the number of lone pairs around carbon. And again, the reason why we say there's a total of 2 groups is because a double bond is considered 1 group. And I know that I kind of flustered that, but I don't want to go back and redo all of this. So remember, the number of groups and bonding pairs, when you have a double bond, you consider this 1 group and 1 bonding pair. So there's 1, 2 groups and 1, 2 bonding pairs with 0 lone pairs around the central atom, carbon. Now let's look at carbonate. So we have carbonate, CO3 2-. Total number of groups, again, would be carbon bound to 3 oxygens. So we've got 3 groups around the carbon. The number of bonding pairs would, again, just be 3, even though there is a double bond in there, because double bonds are considered to be 1 group or 1 bonding pair. Number of lone pairs around carbon is going to be 0. So we have AX3E0. AX3E0 is going to be trigonal planar with a trigonal planar molecular geometry. So what this looks like would be carbon doubly bound to 1 oxygen and singly bound to 2 oxygens for a total of 3 groups around carbon with 0 lone pairs, so trigonal planar. And finally, let's look at ammonia. So ammonia, or NH3, the total number of groups. Now keep in mind that nitrogen is kind of different. Not only does it have those 3 hydrogens bound to it, but in order to complete its octet, it has 1 lone pair sitting on top of the nitrogen. So the total number of groups around nitrogen is going to be 4. The number of bonding pairs will be 3 bonds to hydrogen, 3 different hydrogens, and the number of lone pairs would be 1. So we would have an AXE class of AX3E1, which means its electron geometry, because it has 4 groups, is going to be tetrahedral. That is a mistake. And its molecular geometry is going to be trigonal pyramidal. I am really sorry, guys, for that mistake. It is tetrahedral geometry, not trigonal planar. I'm going to go ahead and show that big old X out here. That is just straight up not true. That is tetrahedral. If it wasn't so late, I would totally redo this, but I have already spoken for so long and I don't want to go back through. So again, that is, oh crap. Okay, there we go, we're back. So AX3E1 electron geometry takes into account those lone pairs on nitrogen, and so it's going to have an electron geometry of tetrahedral with a molecular geometry of trigonal pyramidal. What this looks like then is, and I'm going to get rid of that tetrahedral part just so that you can see the full nitrogen ammonia there. So it's ammonia with 3 bonds and 1 lone pair for a tetrahedral electron geometry. Again, I'm really sorry about that. But the molecular geometry is trigonal pyramidal. It's not trigonal planar because it's not going to be planar. This lone pair up here makes it into that tetrahedral shape, and so it keeps that kind of pyramid shape to it. Tomorrow we're definitely going to be playing with some molecular models and seeing this, visualizing it in reality so that you can kind of wrap your heads around it. So we'll be doing that tomorrow. Now, your homework for the night, because I would like you to do a little bit of homework for me. Could you please write down on a slip of paper fill in essentially the box here for this. I would like the name, the total number of groups, the number of bonding pairs, the number of lone pairs, the AXE class, the electron geometry, and the molecular geometry for carbon tetrachloride, or CCl4. So carbon tetrachloride, CCl4, I would like you to give me and fill in that table for me about CCl4. Do this on a slip of paper, and I'm going to ask for it tomorrow during class. Alrighty, I hope you guys have a wonderful evening. I'm sorry for the mistakes during this, but I hope it still makes sense. We will, again, as always, talk about it during class. Alrighty, and now I need to find my ability to stop. There it is, stop recording. Alright, you guys have a good night.